Welcome to Turing Point lectures on pedigree polytope. In the last session, we went through several important things relating to the membership checking in pedigree polytope. Membership checking problem is to see whether given X is inside the polytope or not, or if not, we need to get a facet which will be separating the point and the polytope. So we have to identify such a facet. Now, of course, the membership problem ends once we say whether it is in or not. But then the separation problem will be the next one to know how to remove that X from our considerations using the facet. So now I will continue where we left in the last lecture. That is, we saw that if the layered network, how it is defined, and then we often start with F4 problem is our beginning, and then if F4 problem is feasible, we define the network corresponding to 4, that is N4 R4, or is the set of rigid pedigrees in P5. And after that, we went on to define the NK RK mu. And as a step in that, we need to have FK feasibility for going further. If FK is feasible, then of course we identify the pedigrees in RK. And then NK RK mu is whether it is well defined, we have to check using a multi-commodity flow problem.
Here, I shall explain the construction of the bipartite flow problem Fk for k greater than 4. We have already discussed how F4 is defined and solved in the video on fat problems. If you haven't watched that, please watch the same before continuing with this video. Here, we consider the steps involved in construction of Fk for k larger than 4. We have an input network which is well defined, and the pedigrees in Rk-1 or the shrunk nodes in this network in the last layer, with the corresponding availabilities given by mu. We add next layer for k plus 1 and consider the link connecting a node U in the last layer in the input network and a node V in the newly added layer. And for each of these links, we would like to know whether there is a corresponding arc in Fk or not. So we have a restricted network for the link L, and that network is denoted by n suffix k minus 1 of L. In this network, we try to see the flow that could be there from U to V, that means along this link. If this flow is positive, then that becomes the capacity of that link. And so the link is now going to be an arc in Fk. So we construct the fat problem Fk with the origins in the last layer of the Nk-1 network and the newly added layer as the destination layer. And then we solve Fk. Fk is a bipartite flow problem, and we can use any known algorithm for this. Motivation for the restricted network stems from the fact the path P plus the link L should form a pedigree path. That is, a generator of RS as well as IJ must be present in the path, and RS and IJ should not be present in P given K-1. That means the same edges should not be occurring earlier in the pedigree path. And P must end in RS because L starts with RS. The restricted network for a given K and the link L is defined formally here. L is given by K colon E alpha and K plus 1 colon E beta, where E alpha is RS, the edge RS, and E beta is the edge IJ. Nk-1L is a subnetwork induced by the subset of nodes in Nk-1 obtained by deleting a set of nodes. So we start like this. We start the set of deleted node D as empty, and we include all those nodes which would be rendering the path to be a non-pedigree path. So such nodes are all deleted. So here the condition A, B, C, D and E, these all are nodes which are deleted to ensure the requirements we saw earlier. And after deleting these nodes, suppose there are some nodes left in the network such that they don't have any generators. We delete those nodes as well, and we repeat these steps until there are no more such nodes. If a node from D appears in any of the rigid pedigrees to any of the stages, we delete those rigid pedigrees as well. So that means the corresponding sunk nodes are also deleted. the subnetwork induced by the nodes that are left or the undeleted node forms the restricted network n suffix k minus 1 L. To find the capacity along a link L, we consider the problem of finding the maximal flow in n suffix k minus 1 L, satisfying non-negativity of the flow, flow conservation at nodes, and capacity restrictions on the available nodes and arcs. The only sink in the network is K E alpha, and the sources are the undeleted nodes in the first stage. That means 4 colon 1 2, 4 colon 1 3, or 4 colon 2 3, and undeleted pedigrees in RL, where L runs from 4 to K minus 2. If we denote by CL the capacity of the link L, that is equivalent to the maximal flow in the restricted network n suffix k minus 1 L. So now we are ready to define Fk. Forbidden arc transportation problem, Fk is defined as follows. The origins in Fk are the nodes corresponding to K colon E alpha belonging to the last stage of the network n k minus 1, and the rigid pedigrees in R k minus 1. And next we consider the availability for these origin nodes. The updated capacity of node U in nk minus 1 becomes the availability for that node, and for pedigrees in rk minus 1 we have mu p as the availability. In this problem, the sinks correspond to the nodes V such that k plus 1 colon E beta has positive capacity. That means the node capacity xv is greater than 0, and they form the demands. Now the arcs in this network, that means those arcs which are not forbidden, are given by uv such that the link has CL greater than 0, or the arc from P to V is such that P E beta is a pedigree in Pk plus 1. That means we need the following. E beta should not appear in P, and a generator of E beta should be in P, and so we get P E beta as a pedigree in Pk plus 1. And the capacity for any of these arcs is given by Cl or mu p depending on which U we are considering. We illustrate the concept that we have introduced and the problem Fk using some examples. We have here exercise B, which is an extension of exercise A, which we considered in the video on fat problems. You may try to construct F5 in this exercise. Notice that the link P4 6:12 is not possible because 12 appears as 4:12, so this link is not permitted. Thus, we have produced 6 pedigrees in P6 such that X is a convex combination of these pedigrees. So, we have an evidence that X is in convex P6. Since the arc P1 to 6:15 has flow equal to capacity, we have an arc going from 6:15 to P1. Since the flow along the arc P1 to 6:25 is 0, we have an arc from P1 to 6:25. But the arc from P2 to 6:12 has flow strictly greater than 0 and strictly less than the capacity 3/8. We have an edge connecting P2 and 6:12. We can similarly find all the other arcs and edges in graph GF. After finding the graph GF, we need to identify the strongly connected components in GF. We would make use of this opportunity to explain Kosa-Raju's efficient algorithm to do this. This algorithm has two passes. In the first pass, we do a depth-first search on the graph. And in the second pass, we reverse the direction of all arcs in the graph and perform a depth-first search on the new graph. And we do this in the decreasing order, the order determined from the first pass. Each DFS tree in this second pass is a strongly connected component. Apply Kosa-Raju's algorithm. It has two passes. In the first pass, we do a depth-first search in the given graph. And then we reverse the graph and do another depth-first search, of course this time starting with the node that has the highest number. It means we are descending, in descending order. We will be processing the depth-first search. And whenever we get a tree in the second pass, we get a corresponding strongly connected component. And this way we find all the strongly connected components in the graph. After identifying the strongly connected components in GF, we find the interfaces and bridges in GF. The interfaces are the arcs connecting any two strongly connected component. In our case, 615 P1 and P1 625 are such arcs. So IG contains these two arcs. And SC1, the strongly connected components SCC1 and SCC2 are singletons, so there are no bridges. And the strongly connected component 3, if we remove any of the arcs or edges, you still get the same. It's a connected component, so we don't have any bridges. In F5, P1615 has positive flow, so that's a rigid arc, and P1625 has zero flow, and that is a dummy arc. This we infer from the interfaces and bridges just now what we found. And so there's only one rigid pedigree given by 413, 512, 615 or 13, 12, 15. That is the only rigid pedigree, and the flow along this path is 1/8, so that becomes the mu of P. So thus we have obtained N5 by deleting the arc corresponding to P1615 from F5 and the arc P1625, which is dummy, so we delete that too. And we adjust the capacity of the corresponding nodes. If the node capacity becomes 0, we remove those nodes as well from N5. If Fk is not feasible, then we can conclude that x given k plus 1 does not belong to convex pk plus 1, and we stop. Now the proof of this is what we'll be discussing next.
Now, if Fk is not feasible, what conclusions we can make? So that's our next topic. If Fk is not feasible, we shall show that x given k plus 1 is not in convex pk plus 1, or it means that x is not in convex Pn. So we can conclude that we don't have to proceed further. So how do we prove this result? That is, if Fk is not feasible, x given k plus 1 is not in convex pk plus 1. Of course, if it is feasible, of course, we saw how we are completing the construction of the layer network. I can just recall that if Fk is feasible, we complete the construction using identifying the Rk, that is pedigrees in Rk. And if a rigid flow from a unique path, then that contributes a rigid pedigree. That means we have a rigid arc and the flow is by a unique path. In that case, we have a rigid flow, and that gives rise to a pedigree in Rk. And similarly, we take a rigid pedigree in Rk minus 1, and there is a rigid arc which is connected to that. And in that sense, we are also getting a rigid pedigree for Rk.
Here we discuss a sufficient condition for non-membership in convex Pn. Fk problem, which we defined and solved, if it is not feasible, then this implies x given k plus 1 is not in convex pk plus 1, and hence not in convex Pn. X is not in convex Pn. So here we'll go through a sketch of the proof of this result. This requires some definitions and some lemmas we have proved earlier. We define a fat problem called inst lambda L, where lambda and L are parameters. We next define this problem. We need lambda from
lambda k plus 1 x, and this will not be empty if x k plus 1 belongs to convex p k plus 1. We define a fat problem obtained from I lambda. I lambda is a set of indices R such that XR is a pedigree which receives a positive weight according to lambda. And we are also given an L between 4 and k. Now we have an ins lambda L problem. First we define the origins in this problem and the destinations in this problem. We partition I lambda based on whether a pedigree XR is such that XR LEQ equal to 1 for some edge EQ and XL EQ is positive. So these R's are this set of R's, we have the name S suffix O Q. Similarly, we have a set of destination S suffix D super S small s, and this is the collection of indices R such that XL plus 1 R ES is equal to 1 for some ES and XL plus 1 ES is positive. So we do have the origins corresponding to different Qs and the destinations corresponding to different S's. We continue with the definition of ins lambda L. We need to define the availabilities and the requirements and the forbidden arcs in this network. So we go by one. If we denote by mod y suffix plus the number of positive coordinates of any vector y, n suffix o will be mod of XL plus. That means the number of positive XL EQs. And similarly, n suffix d will be number of positive XL plus 1 ESS. So we can now define the availability at Q, AQ is equal to sum overall R of S OQ of lambda R's. That means we sum all the lambda R's over R belonging to SOQ. And that should be equivalent to X suffix L EQ for different Q equal to 1 to NO. Let BS, the demand at S, is equal to summing all the lambda R's over R belonging to S suffix D small s, super small s. This should be equal to X suffix L plus 1 of ES for different S's, 1, 2, etc. and D. So we have the forbidden arcs given by F. It is all those arcs Q, S such that S suffix OQ intersection S suffix DS is empty. So there are no common pedigrees between these two sets. Then that is forbidden. The problem with an origin for each Q and availability AQ, a sink for each S with demand Bs, and the forbidden arcs given by F is called the inst lambda L problem. So we are interested in the flow feasibility of this problem.
We use a basic lemma on a fat problem defined on partitioning a finite set in two different ways. Consider two partitions of D, D1 and D2, D1 consisting of N1 elements and D2 consisting of N2 elements. We define a fat problem as follows. Let the origins correspond to D1 alpha with availability A alpha equal to G of D1 alpha for alpha going from 1 to N1. And similarly, we define the destinations corresponding to D2 beta with requirements B beta equal to G of D2 beta, beta going from 1 to N2. Let the set of arcs be given by alpha beta such that D1 alpha intersection D2 beta is non-empty. Then F alpha beta given by G of D1 alpha intersection D2 alpha, which is greater than or equal to 0, is a feasible solution for the fat problem considered. This is the lemma, and it's easy to prove. And see, when we say the arcs are alpha beta with D1 alpha intersection D2 beta non-empty, it means that forbidden arcs are when alpha beta is such that D1 alpha intersection D2 beta is empty. That means there are no common elements. So we apply this to our problem, and we can immediately get the instant flow given by FQS equal to the sum of all lambda r's over R belonging to SOQ intersection SDS. So this gives this flow we will be calling instant flow for the problem inst lambda L. So with this we will be able to prove the rest of the result. we have two crucial lemmas which are useful in proving our main result, the implication of Fk infeasibility. First, we show every x star that is active for x given k plus 1 actually satisfy the conditions stated in lemma 5.3. That is, either p star given L is in RL minus 1 or path p star L is available in n suffix L minus 1 L star L for all L going from phi to k, where L star L denotes the edges E prime such that the Lth and L plus 1th components of x star are E and E prime respectively. We use lemma 5.4 as a basis for proving the lemma 5.5. We use induction on L to prove this result. The lemma 5.5 asserts that our construction of the restricted network do not miss any of the active pedigrees for x given k plus 1. This is important because if we miss any of those active pedigrees, then our construction is useless. So, the proof of these two lemmas are also equally important. The proofs are given in the description. The proof of lemma 5.4 is done considering two cases. Either 4:E4 is not in N4 L phi star, or case 2, 4:E4 is in N4 L phi star, but the path E4 E5 is not in N4 L phi star. And we show both these cases are not possible, and thus either P star given 5 is a rigid pedigree in R4 or it is available in N4 L phi star. And once this is proved, we have a basis for proving lemma 5.5 by induction on L. The proof of this theorem, Fk infeasible, implies x given k plus 1 does not belong to convex pk plus 1, goes as follows. Suppose x given k plus 1 belongs to convex pk plus 1. From the crucial lemma we just now proved, we have the paths corresponding to x r given L available either in n L minus 1 L R or PR given L belongs to R L minus 1 for each R in I lambda corresponding to any lambda belonging to lambda k plus 1 x, and for each R in I lambda, and for each L between 5 and k. So we have the conditions of the lemma 5.3 met, and so the instant flow in the inst lambda L problem is feasible for FL for phi going L to L going from phi to k. So we get a contradiction, hence the theorem. The proof of this theorem, Fk infeasible, implies x given k plus 1 does not belong to convex pk plus 1, goes as follows. Suppose x given k plus 1 belongs to convex pk plus 1. From the crucial lemma we just now proved, we have the paths corresponding to x are given L available either in n L-1 L or P r given L belongs to R L-1 for each R in I lambda corresponding to any lambda belonging to lambda k plus 1 x, and for each R in I lambda, and for each L between 5 and k. So we have the conditions of the lemma 5.3 met, and so the instant flow in the inst lambda L problem is feasible for FL for phi going L to k, L going from phi to k. So we get a contradiction, hence the theorem.
So with that we conclude this session.